what we will talk about in this lecture is somehow independent of what we have seen so far, and it's also independent of what we will see later on, but still we will briefly talk about it because it's simply too beautiful to leave out. Okay, and we'll study it under the title Duality. Okay, for that we have to introduce some notations, some definitions related to graph theory, and then using those definitions we will define finally something that we're going to call a dual circuit. Okay. To be able to talk about dual circuit, first we need to understand what we mean by dual graph. And a dual graph is defined as follows. First of all, not all graphs have duals. Okay, in order for a graph to have a dual graph, it has to be a planar graph. Okay. So we start with a planar graph. Given a planar, non-separable graph, so let's call it G. This is how we construct its dual graph. We construct its dual. Okay. And to indicate that something else is dual, we use a notation hat. Okay. So we put a hat on top of G. So that means this graph is the dual of the original graph G. Okay. Dual G hat as follows. The construction is really very straightforward. Okay. First, assign clockwise direction to each mesh, okay, in graph G, and by mesh we mean inner mesh, and counterclockwise direction to outer mesh. Okay, we'll define what we mean by an outer mesh on a picture. And then let branch BJ be touching meshes and X and Y. Okay, these are those two meshes in our original graph G. And since we're also dealing with the outer mesh, now every branch must be touching exactly two meshes. Okay, and those meshes, suppose for some part of the branch, be called MX and MY. Now, the meshes, they have direction. Okay, inner mesh is clockwise, outer mesh counterclockwise. The branches, they also have direction. And those directions play an important role when we start talking about duality. If the direction of BJ is same as an X, and because again that we're careful about the assigning directions to meshes, that each branch not only touches exactly two meshes, but also it's in the same direction with one, exactly one, and opposite direction with the other. Okay, the same as an X, and if that's the case, then it must be that it's opposite to MY, and opposite to MY, mesh Y, then BJ hat. Now BJ hat is the dual of this branch bj. Okay, bj belongs to g, bj hat belongs to g hat. Okay, if g has b many branches, g hat must also have the same number of branches. Okay, and for each branch that corresponds a dual branch in the dual graph. Okay, and we're labeling that dual branch with this hat notation, bj hat. Then bj hat leaves node nx hat. Okay, and enters node n y hat. Okay, here's another thing. We'll be clear about that later on, but to each mesh in the original graph, there corresponds a node in the dual graph, and that node, okay, is the dual of that mesh. That's what we said. Okay, now this definition at this point seems a little bit abstract, but when we apply it on an example, it becomes quite clear, I hope. Now here is an example. Suppose that this is our okay, 1, 2, 3 inner mesh and 1 outer mesh graph G with 5 branches. Okay, so the branches are labeled as follows. Let's say this is branch number 1, this is branch number 2, this is branch number 3, branch 4, and finally this is B5. Okay, 5 branches with the following labeling and directions. Okay, now we have 1, 2, 3 inner meshes. Okay, let's call them N1, N2, and N3. And here the definition says that all the directions of inner meshes must be clockwise. Therefore, this is the direction of N1, this is the direction of N2, and this is the direction of N3. Okay. To be able to apply this construction, we also have to take into consideration one last mesh, and that's the outer mesh. An outer mesh is this loop that's made of the branches that make the border of the graph. Okay, for the given drawing. Therefore, here we have one last mesh that contains the branches B5, B1, and B4, and its direction is, again according to the definition, is counterclockwise. Okay, so these inner meshes were clockwise, therefore this guy must rotate in the opposite direction. Okay, that's the direction of our outer mesh, and the outer mesh is labeled M4. M4. This is our outer mesh. Okay, and this graph is what we're given. We're calling it graph G. Now what we want to do is we want to apply this procedure and obtain the dual of graph G. Okay, and let's put the dual here. Okay, now the dual is such that here we have 4 meshes. Okay, and to those 4 meshes in the dual there will correspond 4 nodes. Okay, so we can call those nodes N1 hat, N2 hat, N3 hat, and N4 hat. Okay, so 4 meshes, counting also the outer mesh, means 4 nodes in the dual graph. We have 5 branches. For the dual graph, we have also 5 branches. Graph and its dual, they always have the same number of branches. Okay, so this is our G hat. Now, what remains now to construct G hat is to figure out how the duals of these branches, B1, B2 up to B5, appear as B1 hat, B2 hat up to B5 hat in the dual graph G hat. Okay, for instance, what happens to B3 hat? So B3 hat must be between two nodes, okay? And we have to determine what pair of nodes B3 lies between, and also from which node to what node it's drawn. Okay, we also have to determine this direction. Okay, and for that we can apply this very simple construction here. It's not really necessary, but for the sake of completeness or to make things even more apparent than they are, let's employ these very simple tables. Direction of same as opposite to. We have 5 branches, so that means we require 5 rows. B1, B2, B3, B4, and last row is for B5. And here let's make the dual table. Here we have branch, leaves, enters. Okay, B1 hat, B2 hat, B3 hat, B4 hat, and B5 hat. B1 hat, B2 hat, B3 hat, B4 hat, and B5 hat. Okay. Now, by studying the relations of these branches in the original graph to the meshes, we will figure out the relations of these dual branches to the dual nodes. Okay. Now, direction of B1. B1, first of all, is in between two meshes like every other branch. It's between mesh 1 and mesh 4. Its direction is such that same as mesh 1 and its opposite to mesh 4. B2, second branch, is between two meshes M1 and M2. It's same as M1 and opposite to M2. Okay, it's very simple. And then B3 is in between M2 and M3, same as M2, opposite to M3. B4 is between M3 and the outer mesh M4. It's same as M4, opposite to M3. And finally, the last branch, B5, is between M2 and the outer mesh M4. It's same as M2 and opposite to M4. Okay, and then these nodes translate into, these meshes translate into nodes in the dual graph G hat. So B1 is in the same direction with M1 and opposite M4. So according to that construction, we have it leaves node N1 hat and enters node N4 hat. B2 hat leaves node N1 hat and enters node N2 hat. Okay, and so on. N2 hat, N3 hat, N4 hat, and N3 hat. And for the last branch, N2 hat, N4 hat. Okay? Now here is our graph, but let's make it more visual. That is, let's translate this information into a picture. Okay. So here we have B1 hat. So B1 hat is leaving N1 hat, okay, and entering N4. So B1 hat is between N1 and N4, and its direction is it leaves N1 hat and enters N4 hat. Okay, so this here is B1 hat. B2 hat leaves N1 and enters N2. Therefore, this is B2 hat. It leaves N1 hat and enters N2 hat. B3 is between N2 and N3. Okay. So here we have B3 hat. How about its direction? It leaves N2 and enters N3. Therefore, its direction is that. B4 is between N4 and N3. Here we have B4 hat. How about its direction? It leaves N4 and enters N3. And finally, B5 is between N2 and N4. Okay. Its direction is it leaves N2 and enters N4. Okay, it's very simple. That's our B5 hat. B5 hat. Okay. Now, having defined dual graph, now we're ready to define dual circle. And the construction now is as follows. Let N be a circuit with only two terminal elements or a single branch elements, components, and a planar non-separable graph. Which we call graph G. Circuit, or the dual circuit, which we call N hat, okay, satisfies the following properties. Is the dual of the original circuit, and if one graph of N hat is G hat. Okay, G hat is the dual of G, and G is the graph of the original circuit N. Then that's the graph part of the definition. We also have the terminal equation part, and it goes as follows. The branch equation of branch equation of branch B hat of N hat is obtained from its corresponding equation associated to branch B of N by performing the following substitutions. here is what we mean by substitution. Variables of n and variables of n hat. Okay. Now, wherever you see vk, okay, in n hat that becomes ik hat. Whenever you see current, you make it voltage. Okay, so the currents are swapped with voltages and voltages swapped by currents when you go to dual circuit. And as for charge and flux, they're also swapped. Okay, if you have some charge somewhere in the circuit, that charge becomes flux in the dual circuit. Flux hat K, and flux K here becomes charge hat K. Okay. Now this means, okay, this looks a little bit like something complicated, but it's really not. For instance, what we're told here is as follows. Suppose that you have in your circuit an arbitrary branch, and then you look at the branch equation or terminal equation for the component corresponding to that branch. Suppose that it's branch number 3 and the component is a capacitor, okay, excuse me, an inductor. Okay, V3 equals 3 di3 dt. Okay, suppose this is the terminal equation for the third branch, okay, of the network or the circuit N. Okay, and then in the dual circuit N hat, the third branch will satisfy the following terminal equation. This guy becomes just swap voltage with current and this current by voltage. In other words, V3 becomes I3 hat equals 3. You don't touch the constants or other functions. And here this I3 becomes V3 hat. dV3 hat over dt. Okay? From the physical point of view, what happens is, this is the equation describing an LTI inductor, V equals L di dt. And now in the dual circuit, we have I equals something dV dt, that is this LTI inductor in the original circuit becomes an LTI capacitor in the dual circuit. And the relation between inductance and capacitance for the dual component is such that here we have an inductance of 3 henries that describes this component, and that 3 henries becomes 3 farads describing the capacitance of the dual capacitor. Okay, it's very simple. Or V3 equals 3 times I3, let's say. Forget about this di3 dt. So we're talking about an LTI resistor with resistance 3 ohm. In the dual circuit, it becomes I3 hat equals 3 times V3 hat. Okay, again an LTI resistor, but this time, in relation, its conductance appears. Okay, here we have 3 ohms that describe that component. That corresponds to 3 moles in the dual circuit, or 1 over 3 ohms in the dual circuit. Okay, now it's quite straightforward. Now let's apply that procedure to an actual circuit. And for a given actual circuit, let's try to obtain its dual. Okay. Obtain dual of the below circuit. circuit is given as follows. Two sources, two resistors, and one capacitor, one inductor. Plus minus Vs. This is an independent voltage source. Here we have an independent current source, S. Here we have an LTI capacitor with capacitance C, an LTI resistor with resistance R1, an LTD, linear time varying resistor with resistance R2 of T. And here we have an LTI inductor with inductance L. And we also given that EST is 2 cosine T ohms. IST is constant, 2 amps. L, inductance is 3 henries. And what else? The capacitance is 10 microfarads. The resistance, LTI resistance is 10 ohms, and R2T is 2 plus cosine T ohms. Okay, so therefore it's a resistance that oscillates between plus 1 and plus 3 ohms. Okay, so this is our circuit, and for the circuit we want to obtain its dual. Let's do some labeling, because we need to keep track of things, and labeling is very important. By which I mean, let's give numbers and directions to each branch. Okay, so let this be our first branch, and suppose that this is the current. I'm not labeling the voltages, but voltages in our head we can label it easily. We have to obey passive sign convention. That is, if this is I1, by V1 we mean plus here, minus here, V1. Okay. So this is our first component, which in the graph will be represented by branch number 1, because that's how we do the labeling. So that's I1. Let this be I2. Directions are just arbitrary. Okay. This is I3. Let's say. This I4, let this be I5, and suppose that this is our last branch number 6 with fraction, then I6. Okay, this is circuit, and now the procedure here is, from the circuit we will obtain the graph. From that graph we will obtain the dual graph, and then from that dual graph we will construct the dual circuit by both looking at the graph and converting these relations, terminal relations, to the dual relations following this rule here. Okay. Okay, so this can be represented by the following graph. So this is branch number 1, this is branch number 2, this is branch number 4, this is 6, 3, and 5, okay? This branch represents, for instance, the voltage source, this branch represents the capacitor, this branch number 4 represents this time varying resistor, and so on. Okay? Now this is our graph G. Okay, given the circuit, okay, with or without labeling. If it's without labeling, we do the labeling, and then from that circuit we obtain graph G. Okay, The next step is, from that graph, you will obtain the dual graph. For that, let's mark the meshes, because the meshes here become nodes in the dual graph. Okay? We have 1, 2, 3 inner mesh and 1 outer mesh, so that makes 4 meshes. That means in the dual graph you will have 4 nodes. How about the number of branches? Number of branches in this graph and this dual, they are the same. Okay. So this is mesh A, this is mesh B, this is mesh C. By convention, the directions are clockwise. And then we have the outer mesh. By convention, its direction is counterclockwise. Okay. And now it's really straightforward to obtain graph G hat. We have, okay. So all these meshes, A, B, C, D, they translate into nodes. So we have A hat, B hat, C hat, and D hat. Okay. A hat, B hat, C hat, and D hat. Okay. The meshes A, B, C, D, they become nodes A hat, B hat, C hat, D hat in graph G hat. Graph G hat. Now, how about the branches and their directions? So, this is branch 1. It's between A and D. Okay. Between A and D. And its direction is such that it's same with mesh A and opposite with mesh D. Therefore, it leaves A hat and enters D hat. This is our 1 hat branch. Okay, then move to branch 2. It's in between A and B, therefore, here it's between nodes A hat and B hat. Its direction is same with node A, therefore it leaves node A. This is 2 hat. Okay, branch number 3. It's between B and D. Okay, therefore it should be here. How about its direction? It's same with B. Therefore it leaves B. 3 hat. 4th branch is in between B and C. Okay, this is 4 hat. How about its direction? It's same with B, therefore it leaves B. Okay, that's the direction. And 5 is here, it's between A and D. Between A and D, here we have 5 hat. Its direction is, it's same with D, therefore it leaves D. And finally, 6 is between C and D. This is the 6th branch. 6 hat, its direction is the same with D, therefore it leaves D. Okay, so it's quite simple. That's our graph G hat. And now remains the last step, which is from this graph and also looking at those terminal equations, we will construct the dual circuit and hat. Now let me quickly check whether I'm going to mistake here. Okay. Now, circuit N. Now circuit N hat, circuit N hat, we have graph G hat, okay? And the nodes are labeled as such, A, B, C, hat and D hat. So let me put those nodes here, okay? This is A hat, this is B hat, this is C hat, and this is our D hat. Now what we're trying to construct here is circuit and hat. Okay. Circuit and hat. Okay. Now let's go branch by branch. Now, starting from the first branch. Okay. It's between A and D. Okay. So here we have a component. A hat and D hat. Now, since this is not a graph but a circuit, we have to be specific about what component we're talking about. So for that, what we do is we look at the original circuit. In the original circuit, the first branch corresponds to an LTI capacitor. Therefore, in the dual graph, it should be an LTI inductor. Okay. So that's the component for the first branch. And now here we label the currents. Let's now do the dual thing. Here label the voltages. Now here the direction of branch number 1 is from A hat to D hat. That means the polarity of the voltage is plus here and minus here. And that's voltage V1 hat. Okay. And here this is our L hat. Dual inductance. And what's that inductance? Okay. Here the component is C and the capacitance is 10 microfarads. Therefore, in the dual circuit, L hat becomes 10 microhenries. Okay. Okay. Then we have branch number 2. It's B A and B. We look at 2, it's a LTI resistor, therefore here is also an LTI resistor. Okay. Okay. Direction is from A hat to B hat, therefore the polarity is plus minus V2 hat. Okay. Here we have R1, okay, and R1 is 10 ohms, therefore we should have here G1 hat, which will be 10 moles. Okay, third branch is from B to D, and the third branch here is an LTI inductor, therefore in the dual circuit it has to be an LTI capacitor. Okay. With capacitance C hat. And here the polarity is, this direction is from B hat to D hat, the polarity is plus minus V3 hat. Okay. And so, let me quickly place the remaining components. This is G2. This is G2 hat of T, and the polarity is plus minus V4 hat. And then we have here plus minus V5 hat. Okay. Once again, this is the fifth branch. The fifth branch corresponds to a voltage source in the original circuit. Therefore, in the dual circuit, it would be a current source. Okay. Now the question is, okay, let me put here IS hat. Now the question is, what's the direction of the current or the arrow in this source circle? For that, you get the original circuit. In the original circuit here, this current and this polarity obeys passive sign convention. Here, this voltage and this current must also obey passive sign convention, meaning that this is the direction of the current, okay, of the current source. And finally, what remains is another source here, the last source, that corresponds to branch number 6. Here we have branch number 6, the origin circuit is a current source, therefore in the dual circuit it should be a voltage source. Okay. Now the direction is plus minus V6 hat. Okay. This current is in the same direction with the current of the current source, therefore this polarity must be same as the polarity of the voltage source, which is Vs hat. Okay, this is our circuit. And let's also be precise about terminal relations. What we do is we just take this list and dualize it, so to speak. That is, we have Is hat T, then Vs hat T equals something, and then we have L becomes C hat, then C becomes L hat, R1 becomes G1 hat, and R2T becomes G2T hat. Okay? This is 2 cosine T volts, therefore we have 2 cosine T amps. This is 2 amps here in the dual circuit, it's 2 volts, okay? Swapping voltages with currents means swapping amps with volts. Okay? This L, 3 Henry, becomes C hat equals 3 farads. L, C, 10 microfarad, means L hat 10 microhenries, and so on. 10 moles or 10 Siemens, and 2 plus cosine T, again moles. Resistances became conductances here. And finally, what's the relation between this, I'm talking about physical relation of this circuit to this quite different circuit. The physical relation is as follows. At any given time, we would have now we're considering those 2 circuits simultaneously. You would have Vk hat equals Ik. Okay. Voltages here equal the currents there and vice versa. And Ik hat equals Vk for all 6 branches. Now let's generalize what we're trying to display in this example under the title Principle of Duality. Let N and N hat be dual circuits. And let S be a true statement about N. Now, from that statement, S, okay, for instance, okay, one such statement would be in this, okay, suppose that this is the circuit which we dualize. For this mesh something, there are 3 related voltages, V3, V4, V6, okay? And among all those 3 voltages that's related to that particular mesh, okay, let's call it mesh M1. The one with the largest magnitude is V6 hat, and its value equals 12 volts, let's say. And then, so that's a statement. When we dualize that statement, it becomes the following, and it turns out that that statement is also true. For the dual circuit, okay, for the node, okay, if this is mesh M3, let's say, for the node M3 hat, there are 3 currents that's either entering or leaving that node. And those currents are I3, I4, and I6. And among all those currents, the one with the largest magnitude is I6, and it's 12 amps. Okay, so what you do is, when dualizing a statement, you swap all the terms with its dual, and what happens is that dualized statement is also true statement. Obtain statement S hat by each graph theoretical and electrical word quantity by its dual. And by doing that, you obtain a new statement, and it turns out that that new statement is also correct for the dual circuit. Then S hat is a correct statement about N. Okay. Now here is some dual pairs. And by thinking a little bit, you can generate your own dual pairs also. Okay. Node, mesh. Okay. We've seen that node in one of the graphs becomes mesh, and the other from more than mesh. They're dual concepts. Okay. Fundamental, cut set, and fundamental loop. Okay. They are duals of one another, turns out. Reference node or ground node, it's dual with outer mesh. Tree is dual with called tree, unsurprisingly. Voltage is dual of current. KCL is dual of KVL. Okay, that is, here's you write a voltage equation in terms of KVL, and then that equation becomes true from the KCL point of view if you swap voltage with currents for the dual circuit. KCL and KVL are dual. Charge and flux are dual. With a dual pair. Resistance and conductance are dual concepts. Inductor and capacitor. Okay. Inductance and capacitance. Current source, voltage source, and so on. Short circuit, open circuit, and you can add more terms, entries to that long list.